Hello everyone, my name is Rajat Batra and today we are going to do a most important question on binary search tree, that is lead code number 7, lead code 700, search a key in a given BST. It is one of the most important question in the entire binary search playlist. Before starting, you all are aware of a key important point in BST, that if a root has a value x, then all the nodes to the left of root will have a value less than x, and all the nodes that are to the right of root have value greater than x. We will use this property to search a key in our BST. Is this clear? Yes. Now this is the structure of a node given. A node contains three things. First is data, second is a pointer to a left node, and a third is pointer to a right node. Now here is a binary search tree given to us. Firstly, let's verify that it's a binary search tree or not. It's root 4. Then all the values 2, 1, 3 to the left of it are smaller than it, and all the values to the right of it are 7 or greater than it. Now we come to 2. All the values to the left are smaller, and all the values to the right are greater than it. So it's a BST. It is a valid BST. Now what we need to do is we need to search for the key 3 in this, and if the key is present in it, we have to return that node, else we need to return null as our answer. So let's get started. Firstly, each time we will start with root. We are currently here. Now our key is 3. Is this 3 less than 4 is greater than 3? 4 is greater than 3 means we need to go to the side which contain keys less than 4, because if we move to right it will be greater than 4, it will be even greater than 4, as is 4 is greater than 3, all the elements to the right will also be greater than 3, but we need to search for 3, therefore we move towards left. Now we are here. Now we see 2, we compare 2 with 3, 2 is less than 3 means all the elements to the left of 2 will also be less than 3, so we neglect this part and we move to right. Now here our node value is equal to key, therefore we return 3 as our answer. We return this node as our answer. Now if suppose the key is not present, we have same binary tree, say 4, here we have 2, here we have 3, here we have 1, here we have 7. I ask you to search for 5. Key is now 5. Firstly, we are here. We compare 4 with 5. 4 with 5. 5 is greater than 4. Means we need to move to right side, because all the elements to the left of 4 are of no use to us. Because if 4 is less than 5, then all the elements to the left of 4 will also be less than 5. Move here. We compare it with 7. Is 7 is greater than 5. 7 is greater than 5. Therefore, we need to search a key that is less than 7. Therefore, we will move towards left of the 7. But left of 7 is null. Whenever we encounter null, we return null as our answer. Null means key is not present in our BST. Now before moving on to the coding part, let's firstly discuss some of the key points that we have studied before. Firstly, if nodes data is equal to key, means we have found the node. We have found the desired node, therefore we return this node as our answer. Secondly, if a node's data is less than key, means our key is greater than node's data, and in BST all the nodes to the right of that node will have value greater than it, therefore we move to right. Therefore we update our node to node is equal to node correct. Third, if node's data is greater than key, means our key is smaller than that node's data, and all the values to the left of this node will have values smaller than this, therefore we move towards left side, node is equal to node ka left. And last point, note, if at any point in time we encounter null, means key is not present in BST, because we encountered null, and we will return null as our answer at that moment of point. Now let's move on. We have been given a function to complete, that is search function. It return a node as our answer. Now we have given two parameters. First is root and second is key. Root is the root of BST and key is the key we want to search. As I have earlier told that always we will start from root of the BST. We are starting from root of the BST. Now we will run this loop until we encounter a null, because if we encounter a null means key is not present in our BST and we return null as our answer. Now, first condition that we check is if root data equal to key. If that is the case, means we have reached to our desired node. We have reached to a node that we want to search for. Therefore, we return root as our answer. Second, if root data is greater than key, means our key is less than the data currently on the node. Therefore, we move towards left because the key data is less than that of this. If we move towards right, all the elements would have been more greater than the key. Therefore, we move towards left. And if that is not the key, that is root data is less than key. Therefore, we move towards right because we want to move to right because our key is greater than root data. And if in this entire loop we doesn't return anything, means we haven't got our answer and our key is not present, then we return null as our answer. Suppose this is a binary search tree having 15 nodes, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 nodes. Now we want to search a key in this BSP. So what we will do is we will start from here. We have two choices, either we will move to here or we will move to here, but at once we will move to only one path. So suppose we move to here. Now again we have two choices, either we'll move to here or we will move to here. We can't move to both simultaneously or we will return this as an answer. So let's say in the worst case we move to here. Now again we have two choices, either we can move to here or we can move to here. So say we move to here. Now suppose we again didn't find the key, therefore we move to either left or right, move to left, and we return null as an answer. So in the worst case, how many steps we have taken? 1, 2, 3 and 4. In the worst case, we have taken 4 steps. 1, 2, 3, 4. So what is the time complexity? What this 4 is means at a certain height we are traversing only one node. We are not traversing the entire nodes. At a given level we do traverse only each node. So what will be the time complexity? It will be order of height, and we know that height of a binary search tree is equal to log base n, log base 2n. Therefore the time complexity of binary search tree is order of log base 2n, log base 2n. Now it is our time complexity in the average case. What if we have a tree like this? We have a tree like this, 15, 20, 25, 30. In such cases, we have to traverse each and every node. So in such cases, our time complexity becomes order of n. So on an average, in all the average cases, we don't have trees like this. We do have trees in such a way. Therefore, our time complexity is order of log base 2n. And since we are not using any extra space, therefore space complexity is constant. We do have space complexity is equal to order of 1. So I hope we have covered all the important points in this search a key in BST. So watch it thoroughly and you will find it application in many other questions as well. Thank you.